Okay, I'm redoing this video because we just got discombobulated in class. I'm definitely picking some boring data sets in the future, so there's not anything to talk about but just getting through the R code. So I set my directory where my data is. You have to do that first. And then you want to highlight all the libraries that you want to use. And this is just a template showing you how to make some visualizations. But if you read the directions, I think this data that I showed you today with eMechanic is actually nice data because it tells you, there's some artifacts in there that are nice. So I'm going to read that file and recall that this was 3 groups. One was a control, one was a exercising group on a low dose, and one was an exercising group on a high dose. Now I needed to have percent fat mass, and that's going to be total fat mass. This was in this is not in kilograms, I think it was in grams, so I had to change it to kilograms. And then, so that's why I divided by 1,000. And then it divided by the baseline weight. So what percent of my total body weight is fat mass? I'm going to call that percent fat mass, and that's at baseline when they step into the study. Percent fat mass at final would be, that was already in kilograms, so I just used my data thing to tell me what this is. So this is what I did. I went data dollar, and it brought up all these things, and I wanted the fat mass at final and total fat mass at final, and in kilograms, and I saw it right here. What was it? 174 days in kilograms. So I'm going to put that there, and then I just erased this stuff so that I didn't have to worry about misspelling it. And that gives me new columns in my file. So if I go to data, at the very end, I'm going to see a couple columns with percent fat mass at baseline and percent fat mass at final. So if I believe that exercising makes you lose fat mass, what I should see is that a difference in the fat mass at the final level and fat mass at the baseline level. If I have less fat mass at the final level, then this number is going to be negative, which means I have a fat loss. All right, so I'm going to make a new column that has percent fat mass at the end of the study minus percent fat mass at the beginning of the study. So I'm doing this because you might want to mutate some of your columns too, so I'm showing you how to do that. If you go over here, you'll see now I have this change in percent fat mass. Wherever it's negative, they lost fat. Wherever it's positive, they gained. All right. I love this command that allows you to look at data by group. The groups here are 0 represents controls, 1 represents low dose group, and 2 represents high dose group. And I want to just see what the change in percent fat mass looks like in each one of those groups. So I'm really careful on looking at how my data looks like, and that I've labeled my axes. You see me doing this every time, and that's because number one, I forget, but number two, it's a good habit to have, especially for someone like me that doesn't have good attention to detail. Now notice there's 3 outliers here in the third group that lost a lot of percent fat. I told you this is bad. It makes the data look bad, but actually it's a good thing because in part of your project you're asked to look at outliers and explain them. Well, this, I told you also in class that getting into these exercise interventions means that you have you want to lose weight. That's why they go into these exercise interventions. And so it's possible that the people in the high dose wanted to lose more weight, and in addition to exercising, they did cut back their intake. We don't have much control over that happening. All right, so now I want to maybe look at some summaries of like what the means look like. These are kind of tables you want to put into your project. So if you attach the data and do select, if you just did describe data, I'm going to show you what that looks like if I just do describe data. You get this massive amount of information. You can't read anything and it looks like a big mess. So that's too many variables. I don't want to take all those columns. So instead of doing that, I'm going to just select from that data the columns I care about, which is group, age, maybe sex, the gender, and the change in percent fat. So if you're working on the admissions data, for example, you may just want the physical scores, and so certain things out of that. So Control Enter, and then I'll describe that smaller data set, which is much easier to look at. And so you see, like, now I can see the average change in fat mass overall was minus 0.01 kilograms, which is not a heck of a lot. You're not going to lose a lot of weight with exercise, especially if you're walking on a treadmill. All right, next is making the linear regression model. So I would just want to see what change in fat mass looks like with the explanatory variables of group and age. And if I do that, I get this information here. So I can read off of this. I'm used to doing this with you. This is the intercept, this is the coefficient by group, and this is the age. Not the correct way to think about it, but you can think about this as being a prediction model for change in percent fat mass. So it shows here that being the group was the only coefficient, the only term that was significant as a predictor. That's what that's telling me. And is below the p-value. These are the p-values for that variable, and its point is below 0.05. So the strength of the evidence is very strong that being in a particular group actually affected how much percent fat mass you lose. And you also have that the higher the group, the more fat you lose because this coefficient is negative. We're going to go through that in a little bit more concept, but I just wanted to get the R stuff done first. These numbers are important too. It's the R square, which tells you how much of the variation is explained by the model. It's only 5%, so not a whole lot. So there's other stuff going on. So this is the information you get from here. And I took this model, this 0.00263, you see that showing up down here at the bottom of my screen, and I'm going to put it in a scatter plot. Making scatter plots is part of what you have to do. And so you see, again, X is, I'm just putting age and change in percent fat as my scatter plot. You can do other things with your data, which you choose to make scatter plots. You want to look at it. Just like I looked at this GG line plot and said, oh, there's 3 folks here who lost a lot of percent fat compared to the rest of the people in the intervention. This GG method equals LM puts the line of best fit in there, which you did in MA 103 in Excel. And if you look at that, you'll see this is all the change in percent fat on this axis versus age. There doesn't look like there's any trend here. This is my line of best fit, but I just put the other line here so I could show you how to put your regression line inside the picture if you want to. And there's our outliers here who lost a lot of weight. They were older people, which is pretty interesting as well. Going back to why that might be the case, and remember I told you that people who sign up for these studies want to lose weight. They might have just wanted to lose weight so badly that they not only exercised and did a ton of other stuff just to lose weight. In class, we're going to do a thing on correlation, but this is just how to get it, how to get what the correlation is. The closer this number is to 1, the stronger the correlation. And this says the age and group had, they all look pretty low. And they should, because these were randomized, so that you shouldn't see something there that looks like there is a correlation. Now this is how to calculate residuals. You want to take the variable your response variable and subtract off your linear model. And here it looks like that I call that the error because I think of the linear model as being a prediction, which is not the right way to think of it, as predicting change in percent fat mass. If I plug in age and the group you're in, I should get change in fat mass as a result. And the difference between the two is the error between the ability to predict it. That's not really what it's called. It's called the residual. So, but I'm going to keep it as error for now. Conceptually, it's easy to understand. So I need that residual, but the next thing I need is a histogram of that. So if I go to my data file, I'll now have a new column at the end that says error. I should call this residual. Now, if I want to see the histogram, that error needs to be normally distributed, and I went over this in class. It isn't. So I violated the validity condition, or the conditions I need to actually run a linear regression. But let's just keep going. Trend and the error also, you want the data in the residuals to be scattered around 0, because if you're a good fit, then the error will be close to 0 and scattered around randomly. I find it's not. This is my prediction right here. I'm going to take the linear regression model and I'm going to make a new column. And now I have, now here, if I look at over in the very last column, there's a new column called predicted. Those are my predicted values. And this is a change in percent fat mass, and you can see that they're not too close to each other if you look line by line. So my prediction model is not doing well if you want to think of it that way. And then this thing here is a graph of the residuals. So I need this x value for the graph. It's the average between the actual and the predicted. The actual is the actual change in fat. The predicted comes from my regression line. And I take divide that by 2. That gives me the average. So now I have a column that's called x value. And I'm just going to do a LM, a linear regression between the error and the x value. And the r-square should be low, not high. On the other hand, when you look at this, the r-square is 0.8. We haven't seen that good of an r-square yet, which means that my validity conditions violated. This should have been like 0.001, something small, and it's not. Let me just look at that as a plot. And I see here again that the validity, this is not supposed to look like that. And we have these guys down here, so it doesn't look very good. And you might get something like that when you do your own stuff. That's fine. You want to put the plot in there and just tell the truth and say, hey, you know, validity conditions violated even though we tried to go forward with this. And that's what this is saying. There's one more validity condition that we didn't discuss, and that's that you need an equal variances, which I'll talk about in class. But this is how to get the validity conditions out of your R code. Last I did this smoothing thing. This is in your R manual, and you can see what these gray shaded areas are the variance around this line. This is line number 2, which you recall you had these guys as outliers. That's going to drag this gray shaded area around the blue line down. And you can see it's doing that, and it covered up the other two. So this was a messy plot. It doesn't usually look like this. It has to do with the way the data is scattered and the fact that people don't lose that much fat even in a short exercise intervention that they're walking on a treadmill, so they won't lose that. But okay, so this is a redo of what we were trying to do in class.